When we derive the Henderson Hasselbalch equation, the first thing we need to know is our acid dissociation constant and the acid dissociation equation. So for a generic monoprotic acid, the equation is this. So this has a Ka, which is quoted at a specific temperature. So this is something you should know, regardless whether it is any weak acid or if it's a strong acid. Of course, if it's a strong acid, this will go to 100% H3O+. We should also know what this equilibrium constant expression is equal to at a specific temperature. Here is my conjugate acid conjugate base pair. Here's my conjugate acid conjugate base pair. Remember, solids and liquids are omitted from the equilibrium expression. So let's go ahead and just solve for H3O+. Let me rewrite that here. So I have rewritten this here. I'm going to take the negative log of both sides of the equation. Minus log of both sides of the equation, I'm going to have minus log of the concentration of H3O+, minus log of this whole fraction Ka times HA, all of that divided by A minus. So there is a log rule. And the log rule states that if you take the log of products, log AB, it's just nothing more than log of A plus log of B. So I'm going to do the exact same thing with this situation. I'm going to make this the product of A equals Ka and B equals HA over A minus their respective concentrations. So doing that, this will be minus the log of H3O+ minus the log of Ka and plus log of B, but you see I have a minus sign here because I took minus log of both sides of the equation, so that minus sign distributes. So it's going to be minus the log of HA over A minus. So one final derivation of the Henderson Hasselbalch equation involves another rule of logs. And this rule of logs implies the inverse logs, or if you take log of 2, that is nothing more than minus the log of 1/2. So in other words, this log rule states that if you take the log of A over B, and we have a minus sign here, it is nothing more than plus the positive log of B over A. Okay, notice what happens when you take a number, flip it, you change the sign. So you can go ahead and try this on your calculator. You'll find that log of 2 is nothing more than equals minus the log of 1/2. So the sign actually flips when you inverse the number that you're taking the log of. So minus the log of the hydromonium ion concentration is nothing more than pH. Minus the log of Ka is nothing more than pKa. And log of the ratio of the conjugate base over the conjugate acid. You are confused of where the HA goes. Does it go in the numerator or does it go in the denominator? You can always use this acid at bottom or bottom acid. Just sort of a mnemonic because obviously it's a pain to derive this entire Henderson Hasselbalch equation given the equation in Ka. That will abstract a proton from water, establish this equilibrium, and this will have a Kb that's quoted at some specific temperature. So now we should be able to know that Kb is equal to its products over reactants. Remember, we exclude water because it's a liquid. And let's go ahead and solve for the OH minus concentration. I'm going to rewrite this down here. Let's take minus the log of both sides of the equation. So take the negative log of this side, the left-hand side, and the right-hand side. Once I've taken minus the log of both sides of the equation, I'm going to use that rule once again of log of the products. Log of AB equal to log of A plus log of B. So my A, I'll make AB, and I'll make B this fraction, A minus over HA, its respective concentrations. Remember, the minus sign distributes. The minus sign distributes, so it's going to be minus the log A minus over HA, the conjugate base, over the conjugate acid. Now I'm going to utilize a rule from logs, just as before. So you can do this in your calculator. Pick A equals 1. B equals 2, plug in A and B, and you'll realize that the sign flips if you inverse the number inside the log. So taking advantage of this log rule, we will have this situation. Realize that minus the log of the OH concentration is POH, minus the log of KB is PKB, plus the log of the ratio of the acid, the conjugate acid, its concentration, over the concentration of the conjugate base. So here's the derivation of the Henderson Hasselbalch for the situation that involves a weak base. Here is a POH version of the Henderson Hasselbalch equation, and shown previously here is a pH version of the Henderson Hasselbalch equation.